Hi guys, welcome to this video on acid-base stoichiometry and titration. So what I have here is a situation you might encounter in the lab where you have a flask. It contains sodium hydroxide solution. We know that, but we don't know the exact concentration. We want to find out what it is. Or we might want to verify the concentration of a particular sodium hydroxide solution. So what we do is we're going to react the sodium hydroxide with an acid that we know the concentration of. This is called the titration. So first step in this process is taking a pipette, and what we're going to do is we're going to remove a 10 milliliter sample of the unknown sodium hydroxide and putting it into a flask. And then what we're going to do is we're going to be adding small amounts of known concentration of hydrochloric acid in this case until all of the base is neutralized. And we'll know that by using an acid-base indicator. So what we're going to do is we're going to write down first the balanced chemical equation. You can see it here. So for every 1 mole of hydrochloric acid, we're going to be reacting 1 mole of sodium hydroxide, giving us 1 mole of sodium chloride and 1 mole of water. So we'll write down everything we know. So we're going to know the amount of hydrochloric acid that we're adding. We're also going to know the concentration. We also know the volume of the sodium hydroxide solution, but we don't know its concentration. So let's say that we did this and we reacted the acid and we found out that it took exactly 10 milliliters to neutralize 10 milliliters of sodium hydroxide solution. So we know, just common sense, that because the hydrochloric acid is 0.1 moles per liter, the sodium hydroxide must be 0.1 mole per liter based on the fact it's equal amounts. But let's go through the steps and show you how we can actually determine this and prove it. So what we can do is, if I've got 10 mils of hydrochloric acid, so 0.010 liters, and I know the concentration, I can figure out how many moles we have using our molar concentration equation. So here I've got 0.001 moles of hydrochloric acid that we added that were required to react with all the sodium hydroxide. Then I know it's a 1-to-1 mole ratio, so I've got the same moles, 0.001 moles sodium hydroxide. And remember the volume was 10 milliliters. So at the end of the day, I divide the two and I have a 0.10 mole per liter sodium hydroxide solution. That's the concentration. So basically we've shown how to determine the concentration of this unknown. So what we're going to do is look at an actual example. This is the one you have in your workbook. So we have here, we've got 10 milliliters of this sodium hydroxide solution, and it has an unknown concentration, very similar to the situation we had here. It's completely neutralized with 2.43 mils of 0.5 moles per liter hydrochloric acid. And we want to know, what was the original concentration of the sodium hydroxide? So like before, we write down a balanced chemical equation, write down all of the givens. So in this case, what we have here is we've got our 2.43 mils of hydrochloric acid. Remember, we convert it to liters. There's my concentration, 0.5 moles per liter. So we're going to figure out how many moles were required of the acid to neutralize the base. So when I work this out, we used up 2.43 mils. The concentration is 0.5 moles per liter. So we needed 0.001215 moles of hydrochloric acid to neutralize the base. Well, how much base was neutralized? Well, it's a 1-to-1 ratio, and we determined that it's 0.001215 moles of sodium hydroxide. Well, now we know how many moles we have, but I also know the volume. Remember, we started with 10 mils. So I simply divide the two, and we end up with our final answer, 0.1215 moles per liter. And with significant digits, it's 0.12 moles per liter because we have two significant digits in my concentration. So basically, that's how you do that. Now, how do we actually add the acids or bases? Well, to do that, we use a fancy device, or a very precise way of measuring. It's called burette. Now, burette is basically a glass tube, very similar to a pipette. But what it has is different than a pipette. It has a valve at the bottom. And the valve allows you to control the amount of fluid that you can add. So this valve is called a stopcock. So the stopcock, when it is parallel to the burette, it's open, allows the fluid to go out, and when it's perpendicular sideways, it's closed. And the burette has 0.1 milliliter markings on it, gradations. So it allows you to be very, very precise with your measurements. The thing to remember is we're releasing or dispensing volumes from this. So the zero is at the top. So you have to always read from the top to the bottom. Okay, it's very similar to the pipette again. And you could read it to two decimal places. So for example, here, I've got a pipette with some fluid in it, and I can read that it's 9.1, 2, 3, 4, 5, and 6, so 9.6, and just a little bit over. Bottom of the meniscus here looks like maybe 9.63, 9.62. Remember, you're estimating the last digit. And then that's where I started from. And then let's say that I added a certain amount of fluid to do the reaction, and we ended up with a final volume in here of 24 point, let's see, 1, maybe halfway, 24.15 milliliters. So I started here. This is how much we ended with. So I actually dispensed 14.52 milliliters of the fluid. Here's another situation, very similar. This one's a little bit harder to read, but again, the idea is the same. So here I've got 17 milliliters, and it looks like a 17.1. There's my meniscus, and a little bit over, so 17.12. And the final volume here looks like it's 27.567, and not quite 8, so maybe 27.88 milliliters. And so this gives us a volume dispense of 10.76 milliliters. So you can bottom line, we can very accurately measure the volume of acid or base that's required in titrations, the reactions that we get. Now, the thing to know is we have special terms to describe when the acid and base are exactly neutral. We call that the equivalence point. So the solution is exactly neutral. So basically what happens is the pH doesn't change very much, and then near the equivalence point, there's a big change in the pH, and almost suddenly the pH will change. So in this case, we're very acidic, and then very quickly at the equivalence point, boom, the pH will very quickly change, and it's going to become basic. Now, to detect this, we need indicators. Now, indicators work within a certain range, and the midpoint of the range is called the end point. That's the end point of this particular indicator. And what you want to do is you want to match the end point of the indicator to the equivalence point. So you can see here that of all the indicators, the best one to use that's closest to the equivalence point, the neutral point, is bromothymol blue. Its range here is right at the equivalence point. So that's the best one to use for this particular acid when we're neutralizing it. Now, at the bottom of the page here, you've got the steps that we'd use to do this neutralization reaction or titration. So what we have here is we've got our burette, and in this case, we're trying to determine the concentration of an acid. We know the concentration of the base, so it's switched from before. So what we have here, we've got 0.1 milliliters. That's my initial volume of this sodium hydroxide solution. And then we're going to do is we're going to be adding, here we go, this amount of base to neutralize the acid. So the volume that we have, the volume added or dispensed, what we do is we subtract the final minus the initial volume. So we end up with 12.42 milliliters minus 0.10 milliliters, or 12.32 milliliters. So that's how much of the acid, or sorry, the base was actually dispensed into the acid. Now, how did I know when our reaction was complete? What happened was, because we have an acid in the flask and we're using bromothymol blue, it is yellow. And as you get close to the equivalence point, you're going to notice that as you begin to add more and more base, there's a little bit of green or even blue color forming in the yellow. That tells you that you're close to equivalence point. You have to slow down. And then you start adding the sodium hydroxide, the base, drop by drop. And then when you have a nice equivalence point, you have a beautiful green color. If you add a bit too much base, you're going to have a blue color, so you've overshot that, and this is not very good. You want to try to aim for this green color. That tells you that the amount of base that you added exactly neutralized the acid that you have in the flask. Let's take a look at the actual reaction here. So what we have is, we have our reaction. Again, it is with sodium hydroxide and sulfuric acid. So we need 2 moles of sodium hydroxide to neutralize 1 mole of sulfuric acid, giving us sodium sulfate and water. So what we know is we know the amount of base that we added. We also know the concentration of the base. And in this case, we have a little typo. Let's assume it was 0.1 mole per liter. A little typo there. So I know the concentration. And what we can do, we can figure out how many moles of base were required to neutralize the acid. Once I know the number of moles, I can figure out how many moles of sulfuric acid were present originally. So I'll just use molar ratios, and you end up with 0.00616 moles of the sulfuric acid. That's how much I had in here at the beginning. Well, remember, we also knew the volume of the acid. We added 10 milliliters into the flask. So all we do is we divide the number of moles by the volume to give us our molar concentration. So in this case, the concentration of the sulfuric acid was 0.0616 moles per liter. So this is very, very typical for acid-base titrations. You can titrate other substances as well, but the most common substances you do are going to be unknown acid concentrations or unknown base concentrations. So let's try some of the textbook questions that you have and try completing some of these examples as well. And have a great day. Take care. Bye.